Sketch the polar plot of a unity feedback system with open loop transfer function given by g of s equal to 50 upon s multiplied by s plus 1 plus s plus 5 multiplied by s plus 7. And calculate the gain and phase margins of the closed loop system and comment on the stability of the closed loop system. G of s equal to 50 upon s square plus s plus s square plus 15s plus 50, that is equal to 50 upon 2s square plus 16s plus 50. So it is a second order system. We have to find g of j omega. G of j omega equal to 50 upon s. Substitute s equal to j omega, you will get the minus 2 omega square plus j 16 omega plus 50. Therefore, we have to find modulus of g of j omega to get the magnitudes. We'll get 50 upon square root of real part square, that is 50 minus 2 omega square whole square plus 16 256 16 square 256 omega square. This is magnitude. Angle equal to angle of g of j omega equal to minus, because it has no angle, 0 angle for t is 0, for denominator minus tan inverse of the imaginary part, that is 16 omega upon 50 minus 2 omega square. This is up to 2 omega square is less than 50. After that, less than or equal to 50. After that, is equal to minus of 180 minus tan inverse of 16 omega divided by 50 minus 2 omega square. If you tabulate these values, you will get a table of values. Omega modulus of g of j omega, angle of g of j omega. Omega equal to 0 and omega equal to infinity. When omega equal to 0, we substitute 0 here, 50 by 50, that's why 1 you will get. Angle, when omega equal to 0, if we substitute omega equal to 0, tan inverse of 0, that is 0. Angle also 0. When now infinity by infinity, if you differentiate numerator denominator with respect to omega, you will get omega in the denominator. That's why it becomes tan inverse of 0. It is therefore minus 180. Minus 180 degree. When omega equal to 1, we will get 0.98. The angle is minus 18.5. When it is 10, its magnitude is 0.22. Angle is minus 133. When it is 20, magnitude is 0.06 and the angle is minus 156 degree. When it is 30, magnitude is 0.02 and the angle is minus 164. When it is 40, The magnitude is 0.01. All are negligible. Magnitudes are negligible. Angle only 168. When it is very large, it becomes 180. So we have to draw the plot. You have to draw this on a polar chart. This minus 90, minus 190, minus 270, 360. Clockwise is minus 180. So when omega equal to 0, the magnitude is 1, the angle is 0. When omega equal to 1, it is 0.98, the angle is 18 degrees. Here, when 10 is 0.22, the angle is 133, almost here. So when 120, 156, so it approaches like this. So this is the plot, polar plot. Then we have to find the gain margin and phase margin. We have to find the gain margin and phase margin. Gain margin equal to the magnitude at 180 degree. At 180, the magnitude is 0. Therefore, infinity. Gain margin equal to infinity. When it's at 180 degree, the magnitude is 0. Therefore, 1 by 0 equal to infinity. Phase margin equal to where it crosses unit circle. This is here the magnitude is 1. The unit circle is this. This is the unit circle. Here it crosses 1. Therefore, when it crosses unit circuits, that is 0 dB. 0 dB, how you got? 20 log 1, that is equal to 0 dB. So the 1 is in linear scale, it is 1. That's why unit circle. At the unit circle, the angle is 0. At this point, the angle is 0. Therefore, phase margin equal to 180 minus angle at the unit circle. Angle at the unit circle, that is equal to 180 minus 0. 180 minus 0, that is equal to 180. 180 degree. Phase margin equal to 180 minus angle at the unit circle. Unit circle, that is equal to 180 minus 0, that is equal to 180 degree. Gain margin equal to 1 upon magnitude at 180 degree. Here 180 degree, magnitude at 180 degree is 0. Therefore, 1 by 0 equal to infinity. This is in linear scale. In logarithmic scale, it has to cross 0 dB. Instead of unit circle, we have to say 0 dB. That's all. Polar plot. Now let us see how to draw polar plot using MATLAB. Set of instructions to get the polar plot. Clear all variables are cleared. This CLC will clear the screen and numerator equal to 50. Denominator coefficients are 2, 16 and 50, second order system. 2s square plus 16s plus 50. So now we have to create the transfer function, that is equal to tf n comma d numerator comma denominator. So once we get the transfer function, we have to call Nyquist, because polar plot is part of Nyquist. We have to pass the transfer function, that is this. You will get real part, imaginary part, and omega. To get magnitude of absolute value of real part plus imaginary part dot star I, because it is imaginary part. So you will get magnitude. Similarly, you can get angle equal to angle of real part plus imaginary part dot star I. So you'll get magnitude and angle. It is a three-dimensional array. We need the third column. That's why you have to find the size of this angle. That is y equal to size of the angle A and G. That is equal to that is available in y. So we need the size of the third column. That is y equal to y of 1, 3. You will get the size here. So now we are going to get the three-dimensional array into single-dimensional array. That is mag 1 equal to magnitude of 1, x. Angle 1 equal to angle of 1, x. So you will get the magnitude and angle. Now you call polar angle, magnitude. That's all. So if you call this, you will get polar plot. So now we have to call this file. The file name is the program file name is MATLAB. Yes, we got the polar plot. It is similar to what we draw analytically. Now we have to find the phase margin and gain margin. For that, call margin. We have to pass the transformation. So gain margin is infinity, phase margin is 180. So